In this video, I will talk about clamper circuit, its classification and basic working principle of a clamper circuit. So what is a clamper circuit? Clamper circuit is a network that consists of diode, resistor and capacitor, and it shifts the DC level of any AC signal or alternating signal. So a clamper circuit is a circuit that consists of diode, resistor and capacitor, and it will shift the DC level of any alternating signal. Remember that a clamper circuit does not change the wave shape. If I apply any sinusoidal waveform in the input side, I will get another sinusoidal signal in the output side, and it does not change the peak to peak value. Another thing is that if we want to make any further shift in the DC level, we can do that by adding an external bias voltage either in positive direction or in negative direction. Now let's say I have an alternating voltage. This is a sine wave and it has a positive peak plus 5 volt and negative peak minus 5 volt. Therefore it has a peak to peak value of 10 volt. Okay, now let's say I have applied this sine wave into a positive clamper circuit. Our positive clamper will push up the DC level of this alternating voltage in a way such that its negative peak touches the horizontal or this time axis. Okay, now see, this is the output voltage of the positive clamper. Our DC level was at 0. This positive clamper pushes up our DC level of the alternating voltage in such a way so that its negative peak touches the horizontal axis or here the time axis. Therefore this positive peak will be at a level of 10 and our DC level will be at plus 5. Now I can conclude that positive clamper lift the input wave upward so that the negative peak touches the ground or zero level or horizontal axis, and a positive clamper will shift the DC level of any alternating voltage in upward direction. Here the DC level was at 0, but here the DC level is at plus 5. Therefore positive clamper will push the DC level in upward direction. Okay, now let's say I have another alternating voltage. This is also a sine wave. It has positive peak plus 5, negative peak minus 5. Therefore peak to peak value of 10 volt. Now if I pass this input voltage through a negative clamper, our negative clamper will push the, at first look here the DC level is at 0. If I pass this alternating voltage through a negative clamper, our negative clamper will push down the DC level of this alternating voltage in such a way so that its positive peak touches the horizontal axis or this time axis. Now look at this waveform. If the positive peak touches the 0 level, our negative peak will be at a level of minus 10. Therefore our ground or DC level will be at minus 5. Now look here, the negative clamper shift the DC level in downward direction and our positive clamper shifts the DC level in upward direction. That's it. Negative clamper pushes the input wave downwards so that the positive peak touches the ground level or zero level or horizontal axis, and negative clamper shifts the DC level in negative direction. Now one thing I have to conclude that, see here I am applying a sinusoidal voltage in the clamper input. In the output I am getting another sinusoidal voltage. It has a peak to peak value of 10 volt. Here we have also peak to peak value of 10 volt. So a clamper circuit does not change the wave shape and also the peak to peak value of the input signal. Okay, now I will talk about the working principle of a clamper circuit. A clamper circuit consists of a diode, a capacitor and a load resistor RL, and the clamper circuit working based on the charging and discharging of the capacitor. The capacitor is charged when the diode is in forward bias and discharged when the diode is in reverse bias. Now let me clarify. This is a basic structure of a clamper circuit. If the diode is in upward direction, that will be a positive clamper, and if the diode is in downward direction, that will be a negative clamper. Okay, now if I am applying an alternating signal here, during the negative half cycle, this terminal will be positive and this terminal will be negative. Therefore this diode will be in forward bias, and usually when a diode is in forward bias, we can replace that with a forward resistance RF. Usually the forward resistance of a diode ranges from 1 ohm to 25 ohm. Let's say I have considered the 1 ohm RF forward resistance of this diode. Now a current I will start flowing through this wire. Now when this current gets into this point, it will see two resistance. One is this way and another is this way, and we know that current always follow low resistance path. Therefore all current will flow through this path and this capacitor will get charged. So when this diode is on, we can replace this diode with a short circuit or a path of very low resistance. Therefore our capacitor will get charged. As the capacitor is getting charged through this way, we can calculate the charging time constant here by using the forward resistance of the diode and the value of the capacitor. Here the forward resistance is 1 ohm and the value of capacitor is 10 to the power minus 6. Therefore time constant will be 1 microsecond, and it takes 5 times more than for the capacitor to get fully charged. Therefore our total charging time will be 5 RFC, 5 microsecond. Therefore I can conclude that when the diode is in forward bias, our capacitor will get charged instantly. Now during the positive half cycle, this terminal will be negative and this terminal will be positive, and when this diode is in reverse bias, we can replace this diode with an open circuit as if it does not exist in this circuit, and now our capacitor is holding a voltage VC across it. Now when the diode is in reverse bias and act as open circuit, therefore our capacitor will be discharged through this load resistor RL. Therefore our discharging time constant will be RL into C, 50 kilos, so 50 into 10 to the power 3 into 10 to the power minus 6. Now look, our discharging time constant is 50 millisecond, and it takes 5 times more times for the capacitor to get fully discharged. So I can write 5 RL into C. See, it will take 250 milliseconds or 0.25 seconds. That means it will take 0.25 seconds for the capacitor to fully discharge through this load resistor RL. That means during the positive half cycle of the alternating voltage, the capacitor will hold up a voltage of VC across it. And the operation of a clamper circuit is based on the principle that the charging time of a capacitor, see here the charging time is 5 microsecond, is made very small compared to the discharging time of the capacitor. If I can show that the charging time is much smaller than the discharging time in a circuit consisting of a diode, capacitor and a resistor, I can expect that circuit will act as a clamper circuit. In my upcoming lectures, I will talk about positive clamper, negative clamper, and I will show you several examples using positive and negative clampers.